My dear student, colleagues, and all the viewers who are watching this program live from Facebook page, Physics Center, and School of Astrophysics and Astronomy, and YouTube channel, Pretam Kumar, I'd like to welcome you all to our International Physics webinar. So, good evening to all here in Bangladesh, and good afternoon to all those who are watching this program live from UK and Portugal. So I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar, and we have successfully completed our 206th international physics webinar. And today it's our 207th international physics webinar. So we are trying to adjust with this new normal situation. Today, we would like to welcome you all through a joint session between our department, Department of Physics, Pabna University of Science and Technology, and the Department of Institute Superior Technique, the engineering faculty of the University of Lisboa, Portugal. And we have with us here today Dr. Pedro Abreu, LIP physicist and outreach coordinator, International Particle Physics Outreach Group, Portugal, and associate professor with the Habilitation at the Physics Department of Instituto Superior Técnico at the engineering faculty of the University of Lisboa, vice president of the Physics Department of the Connection to Schools, Portugal. And we have already connected with him. So I'd like to welcome our speaker, sir. Good afternoon, and thank you for joining with us. So, dear viewers and students, I think you have already come to know the title of this today's International Physics. So, the title is A Voyage to the Universe. Very exciting title. I think you will enjoy it. So, you can also join with us using this link, and you can also ask questions by commenting in Facebook and YouTube. So, sir, it's your time. You can start your session. Thanks again for giving us this opportunity.
Thank you very much. Thank you very much, Dr. Pretam. Let me start by thanking you and the University of Pabna to allow me to speak to your students about exciting topics in modern physics, more specifically about the structure of matter, the science call it particle physics, and what we know about it today, and what we don't know about it today, and how this leads us to the understanding of the structure of the universe, or not understanding at all the structure of the universe. So the next 45 minutes, I'll bring you to what we know today from a historical perspective, and I will take questions at the end, but I will ask Dr. Pretam, please, if I'm speaking too fast or too low, or you want to interrupt, please do so anyway, anytime, okay? Just let me know if I have to speak slower or louder or adjust some screen properties or whatever. So let's start.
Okay, sir. Thank you.
We are starting by discussing the universe, and this is a fantastic picture from the Hubble Space Telescope of its deep field camera, which brings us a fantastic view of the universe that we don't see from Earth, but this telescope can capture these fantastic images. Then the universe is what we will discuss today. But I will just like to remind yourselves that this is our universe. It's not a multiverse or universes in other dimensions that we don't know nothing about, but we are discussing our universe, the one we live in, this one that surrounds you, planets, stars, dust, light, and the Higgs field, as you will know in the course of this talk. And when you see this picture of our universe, the stars and the galaxies, I think the most striking question is why? Why is there matter at all? Why are we here? Well, you are there probably because your teachers are obliging you to follow this talk. But let me pose the question in a more ambitious manner. Why is there a planet at all? Why is there human beings? Why are there molecules? Why did atoms organize in such manner and create stars and galaxies and the planets and human life, conscience and thinking? And let me also remind you that in science, why questions are not made. We don't ask whys because we cannot answer them. There is no chance to answer why questions. The only questions we are allowed to ask in science are those that can get an answer from observation and experimentation. So the questions are more what is there, and how it works. And so in the course of this talk, you will find out what we think is there at the smallest scales and how they work together to build our universe the way we see it today. And this is a question that is long dating, comes from very long time ago. Already the Egyptians, indeed, you can see this picture in the tomb, inside the pyramid, where the Egyptians described the universe as stars, these 5 planets known at the time, and life on Earth beneath it. And you can see that the planets and these closest stars do not fall upon ourselves, do not fall upon men, because there is a god, a goddess in this case, a goddess of the skies that protects us from the stars falling upon men and women. And the Egyptians call it Nut, the goddess of the skies that protects life on earth. And it's quite, well, it's a perspective. It's there. It was their view. But I'm trying to bring you, and I need today that you use your brains to go along with me in my reasoning, that you're trying to understand the universe not by recurring to gods or to, let's say, entities that we don't have access through observation and experimentation, but by our observation and by our thinking, by our pure reasoning. And this has had a revolution when I call it the birth of pure reasoning, when people in many places in this globe, in this planet, but those that come to be known are these people, Tals from Miletus, a small village in the coast of Turkey, which was in the 7th century before our era, was part of Greece. And this mister affirmed, looking at things around him, but mostly from pure reasoning, that everything was made of water. You can laugh today, of course. Of course, not everything is made of water. And there were following times that other elements were proposed. 200 years later, it proposed that everything was made of indivisible things, call it atoms. And even this atoms idea was born earlier than these 2 Greek philosophers, in closer to your region, in India region, around the 6th century before our era, was already, this atom hypothesis was already being divisible, being thought of. So things made which cannot divide themselves into smaller things was the basis of the constituents of all the matter around us. And more or less in parallel, about these times, another person, Empedocles, also proposed that everything was made only of 4 elements. Look at this number, 4. It's so small. You can have millions and millions of things around you, different things around you, and everything is reduced to only 4 elements. This was the view of this person 2,500 years ago. And it's funny that still today, you get these 4 elements as given enormous importance in some, let's say, in some philosophers, on some groups in society, but of course it makes no sense anymore. This was the view, well, 2,500 years ago. And it didn't even last for long, because 200 years later, this great Greek philosopher added the 5th element, which is crucial, because without this 5th element, planets made of rock, like Earth, would fall upon us. So planets and stars are not falling upon us, ourselves here in the Earth's surface, because they are not made of these four elements, they would be made of a fifth element, which would be which not suffer gravity, but would suffer anti-gravity, so would not be attracted to Earth, they would not fall to the ground, they would still live long time up in the air. Now, all these people came to these conclusions mostly based on pure reasoning, without much observation and very little experimentation. The experimentation is something that happened very, very often and very early on, already at these times, mostly in Asia, so closer to your boundaries. But in Europe was only in the Middle Ages that people like these represented in this picture, the alchemists, were trying all types of experimentation. So only in the Middle Ages, sometimes also call it Dark Ages, because of the lack of ideas, let's say, or liberty to discuss ideas. But these people in their secret laboratories, not to be, secret because they didn't want to be put to fire, so they experiment every type of experiments. They did carry a lot of experiments, but they didn't have yet a good model of what to experiment with what. So why to mix substance A with substance B? No idea. Maybe because it was not yet tried. So they were trying to mix some things. Of course, some mixings went badly, like exploding objects or freeing deadly gases. But they had no idea to what experiment with what. That comes only later. And in this, I want to discuss the revolution of the scientific method that somehow starts with the models by this Mr. here, Nikolai Copernicus, which published the book, he ordered the book to be published on the year that he died. You see, he wanted to die of natural causes, so he didn't want to come up with a book that would probably grant him to be killed in the fire, by fire. So he called this book The Revolution of Celestial Orbits, to discuss that Earth was no longer the center of the universe, the sun was at the center, and the objects were revolving around the sun. And because this word revolution became to be used, it was so innovative idea that nowadays we use the word revolution for innovative processes in many different contexts, in many different, when we speak of revolution of society, or revolution of the internet, of the industrial revolution, information revolution, we call all these revolutions. But remember, this word revolution started in this book by Copernicus of just things revolving around the main star. Taking the Earth out of the center of the universe is very revolutionary idea, because then it starts questioning why religions want to give such importance to man and to humanity in the Earth planet, and what about the other species in the other planets or in the other stars? Were they visited by Buddha or by Christ or by Mahomet? I have no idea. I don't know of any other civilizations to outside Earth to ask them about it. So, but this, of course, was quite a courageous idea to put forward. Well, courageous. The book was published only after he was dead, so it didn't reveal a great courage, but it did reveal a great innovation of ideas. And when you have these models to explain the observations, the position of the planets, and he constructed complicated models to adapt to his heliocentric view of the universe, but with more data and a lot of more data taken by Tycho Brahe, an astronomer working in Denmark, some data started to be discrepant even with this heliocentric view. And this calls to the birth of the scientific method. So nowadays, we do develop models, theory, that we must confront with observations. If the experimentation of the observations confirm the theory, so much the better. We keep performing new experimentations, new experiments. But if they do not validate the theory, if they find errors in the theory, so much the better, because then we have to develop new theories, new models, new ideas. So this, what we call today the scientific method, is the true basis of all science. And it all started with some sayings by this person here that said in Latin words, cogito ergo sum, meaning I think, thereby I exist. Of course, in some countries in the world, if you exist, you better not think too much because it might turn badly on your door. But this is basically the basis of our process, of our scientific method, that we only have indisputable sentences that we do not put in question, like this one, I think thereby I am. And from these sentences, our reasoning and experimentation are the only way to get to the proper knowledge, what we call the truth. But let me remind you also that this is only the scientific method for the science that we develop. It's nothing to do, not all knowledge is scientific knowledge. There is a lot of knowledge which is not scientific, and it's not science because it's not based on a scientific method, and still is very good knowledge. Music, for example. The musicians do not care about the scientific method very much. They care about what they like, how they express their emotions. And the people that listen to their music, of course, they like the music for the emotions, not for the variation of the waves of pressure, of air pressure, that resonates with their ears. They don't care about it. They care about the emotion feelings they feel when they hear the music they like. So again, not all knowledge is scientific, nor needs to be. It makes no sense. I'm talking only about the scientific knowledge. And it's about science that we talk when we learn that Kepler waited 18 years, 1/8. So he waited 18 years to develop his theory of movements of planets that stopped to be circles, which was the perfect movement. So he gave up the perfection in the skies. So the movements were elliptical. Elliptical are not circles. It's a rather complicated mathematical curve. So Kepler was so fiducial of his perfect skies that he needed 18 years to be convinced otherwise, that the movements of the planets around the sun were not perfect, were not circles, were not regular curves, were elliptical, a rather complicated curve to be described mathematically. And also Galileo experimented with experiments, mostly thought experiments and not real experiments, but with some experiments that build up the laws of mechanics on Earth. And finally, a genius from the same times, about 17th century, that described that the laws governing the planets and the laws governing the objects on Earth were exactly the same laws. And the same laws that explain why the moon is falling upon us every day. Well, before you go out in at night to find out if the moon is really falling, well, the moon is really falling, it is also going forward. So it goes forward a little bit, and it goes down a little bit. It goes forward a little bit, goes down a little bit. And Newton computed what movement would have the moon by realizing how much the moon would have to fall after going forward on a straight line, how much the moon would have to fall using triangles. And he published this law, following these rules, in his famous book, the Principia Mathematica, which for most physicists, certainly for me, describes the starting of physics as a discipline, the mathematical principles to explain the philosophy of nature. Now, some legends and urban myths talk about the tree of the apple that fell upon Newton's head. Of course, this is only a legend. The tree is there in the University of Cambridge, but the ideas of universal gravitation is not related to the fall of an apple. That's just a legend. It is not proven at all that the laws come up with such facility and speed. Now let me advance another 200 years and describe what we want to talk today, what are the smallest constituents of matter. 200 years to talk about Mr. Mendeleev, which was a chemistry. I also like chemists, let me tell you. So he was a chemist, and he proposed that all substances around us are made of actually these indivisible elements, called atoms. So it was recovering the idea from the Greeks, such as hydrogen, calcium, and a lot of other atoms in here. Let me show you atoms. So these are xenon atoms. Xenon is a noble gas. So xenon atoms on a zinc plate. So every blue dot here is a xenon atom. And xenon is a noble gas, and this picture was made possible by this research laboratory of this computer company. You might have heard of this computer company. And in 1989, they were able not only to picture the atoms, but also to manipulate them one by one to make these letters. A more precise image was here made by a Chinese laboratory 10 years later, where they used iron atoms on top of a copper plate. And here I put a picture of the water molecule of one oxygen atom and two hydrogen atoms. So what this Mr. proposed was that all substances made of atoms, the atoms list was this table. So this table he published in 1869, almost 150 years ago, more than 150 years ago, 152 to be precise. And you can see, does this table hold? Does it make any sense? And now you know better, but remember, in 1869, there was no such thing as electrons or a good justification for the existence of these atoms with such regular behavior with oxygen or with hydrogen. So it could be that only by coincidence that these atoms, these elements, are arranged in such way. And then these holes would have no meaning. But if this table bears any significance, any importance, these holes should be filled with elements not yet discovered. And the good thing is that these elements were actually discovered later on. This one is gallium. This one is technetium. I did not put there. But this one, helium, we didn't even know there was a hole here. So this helium existing in our sun. Then, if the table makes sense, a much more profound question is why? Let me tell you, we don't ask why, but let me ask a why. Why are all substances, all atoms behaving in such regular manner? And probably you learned that already in high school. It is about electronic distribution. But electronic distribution needs electrons in atoms. But wait, were the atoms not indivisible? Of course, if they have electrons inside, they cannot be indivisible, but must be divisible in smaller things. So what are the atoms made of? That's what the conclusion from this table, after the discovery of electrons, naturally, but what atoms are made of. And we know better today. So I put here the question what atoms are made of, and depict the average radius of electron's orbit to tell you that what constitutes most of the atoms is absolutely nothing. Nothing is there. Well, there is a nucleus, but it is so small that I have to multiply by 100 to get this white dot. This percentage of the volume of the atom is absolutely nothing. So it is useful information if you want to speak to an older brother or to a colleague. that you heard in the talk that 99,999,999,999% of his brain is totally nothing. It's totally empty. It's nothing there. Well, if this is the one driving you to a party, you would not want to tell him right away. But I like to use another scale. I use the scale of a football stadium. Especially now there are a few championships going. Euro 2021 championship, the Copa America in the Americas is going as well. So it's a good analogy to use a football stadium to talk about the atom. So if the atom would fill, the electrons movements would fill the entire stadium, including the grass area. So the electrons are not doing this tricky trajectory. They are moving all over the place. What would be the size of the nucleus? Well, a pinhead at the center of the field for the smallest nucleus. For the largest nucleus, could be a marble or a ping pong ball, but much smaller than a football ball. So remember, it's not looking to a ping pong ball or to a marble or to a pinhead. It's looking at that at the center of a stadium. That tells you the proper scale of the nucleus. So atoms are made of electrons, of void space, and of nucleus. And what are these nucleus made of? And this is a fantastic question discovered by this gentleman here. Oops, it's too well, went a bit fast. So what this gentleman discovered with an experiment atop a table, two people and an experiment on top of a table, they discover that indeed the atoms are made of electrons surrounding a nucleus, that in the nucleus we have, positive charged particles, call it protons, and neutral particles, call it neutrons, that there is a force between the protons which is repulsive, electric force, which is enormous, equivalent to the weight of 23 kilograms. I don't know if you use kilograms or pounds. I would imagine that in pounds this would be about 46 or 48 pounds, maybe 50 pounds, around 50 pounds. But wait, why is there nucleus? And so they discover immediately that for there to be nucleus, there must be a strong force, a force much stronger than this electric force. So by 1932, the constituents of matter were again four, quite a coincidence, the number four. Neutrinos, I leave this to discussion, I have no time to talk about neutrinos. Electrons, protons, and neutrons. A very simple model that explains all atoms, take into account that atoms explains all substances. The only problem is that if this is the list of elementary particles, later on in the 50s, we discover many more elementary particles like these ones, but many more, like 270 more elementary particles. There are so many that we classify them as hadrons, particles subject to the strong force, and divide them in two classes, the mesons and the baryons. The mesons decay, leaving nothing out, leaving electrons and neutrinos out, whereas this right class, call it baryons, they leave always a proton at the end of the chain. So they decay into other particles until there are only protons. And the proton is absolutely stable. So this raises new questions. What's the new base structure of matter? What are the true elementary particles? Cannot be the proton, the neutron. This would make no sense, because then we would have 270 instead of 4 elementary particles. So we need a new periodic table of smaller constituents of the proton, the neutron, and all these other, animals. And then, while we build the structure to construct these particles, we also need to answer, why is the proton so far absolutely stable? And so the model that came up in 1964, verified over and over, is that the protons, neutrons, and all the other particles are made of quarks, antiquarks, and gluons. Quarks and antiquarks are particles of fractional electric charge, and they came out with a color. Well, nobody sees these quarks isolated, so actually we cannot tell if they are red, blue, or green. So this is just an analogy. But it's a very good mathematical analogy, because then what we say is that the particles that then exist in nature, built of quarks, they must be colorless, must have no color whatsoever. And then we can have this left class, the mesons, built of quarks and antiquarks, like the pair here, a down quark and an anti-down quark, with a color blue and a color anti-blue, would be yellow. So the color would annihilate, or by mixing three colors. By mixing these three quarks, each one each color, we also know this will become colorless. We'll leave color out. And also the charge of the proton is well explaining. 2 times above plus below is 3/3 color, is charge plus 1, so the opposite charge of the electron. Also the neutron with 2 down quarks and 1 up quark is very well explained to have charge 0. The model is a bit more complicated because there are also many more particles in the proton. These cords connecting these quarks we call gluons, from the word glue, that glues the quarks in the proton or in the neutron. So we call these the gluons. So the true model of fundamental particles and interactions, well, we call it the standard model, but of course it's only the standard model in particle physics. I imagine that in biology, the standard model will be a total different thing, which I don't know the name of, or what does it mean. But in particle physics, the standard model means this model of fundamental particles and interactions. And if you want to download this poster, you can go to this link and also print the poster, get the PDF file and print the poster and put it in your room. I'm sure it would fit very nicely next to the poster of your favorite musician or of, I don't know, rock band. And it will be much better when we invite that special person to go visit your room. You could talk about, I imagine the conversation starting like your best friend asking you, oh, you also like this rock band? Fantastic. What's your favorite music? And then they see this poster. Oh, cool. What's that? And then you talk half an hour about particle physics and you win your day. Now let's go into this table. Well, because this poster does not have many elements. Actually, we only know of 12 particles. And for each particle, we also know of its anti-particle, the opposite charged electron that we call the positron. It's known to exist. Also, actually, we have found that for all these 12 particles, we found already their 12 anti-particles. Now, this is the dates when they were first discovered. Well, the electron in the end of the 19th century, and the last particle to be discovered, this type of neutrino, discovered only in 2001. Now, one striking thing is that I was talking about atoms, protons, neutrons, quarks, but the protons and the neutrons are built from these 3 type quarks, UUD or UDD, meaning that only the particles in the first family are needed to build the world around us, to build the matter around you and the planets and the stars. So why did nature, again, a why question that I should not make, but I don't resist. Why did nature brought us this second family of particles? I have no idea. Why the third family? Beats me. Why is there not a fourth family yet? I don't know. We didn't discover it yet. So we have no reason yet why there are 3 families of particles and only 3. And then look at these values in the middle column. The right column is the charge, electric charges, but in the middle column it's mass. Mass in these strange units of GeV over c squared. Let me talk very briefly about these units of mass, because in this last year, there was approved a new international system of units in which all units, all base units, are related to fundamental constants of nature. So the second is related to the atomic transition in a stabilized, excited cesium atom. So it's very, very precise. It's the frequency of that transition in an atom subject to a voltage difference, to a laser interaction. So the second is very, very precisely defined. And then the meter is defined over the second by using the constant speed of light in vacuum, in the void space. So all new base units are totally redefined, only solely requiring the knowledge of these fundamental constants of nature, in physics mostly. Speed of light, Planck constant, the h is the Planck constant, the k is the Boltzmann constant. Well, you'll get to know E is the electric charge. You'll get to know these electric charge of the electron. You'll get to know these if you follow a physics course, or if you're following already a physics course. I'm sure these are very well known to you. Now, how do these fundamental particles interact with each other? I mean, the ones in this table. How do they interact with each other? And this, I use the image of a ping pong game. The ping pong players actually exchange this white ball. But you see the white ball because I use a picture. This is from the Olympic Games, the gold medal attribution game in the Beijing 2008 ping pong game finals. I mean, if I was using a movie, or if you would be there in the pavilion, you would see no ball at all. You just would see these people moving very fast, and nobody would see it. I doubt that even the referee would see the ball. I'm sure he wouldn't, because the ball is moving very, very fast. Now, we also don't see the particle exchanged, but we do see the effects on the particles interacting with each other. So which interactions do we know of? I mean, fundamental interactions. Well, we know about gravity. It's why you fall down when you triple. It's why it's an interaction you come to know first when you are about 9 months age, before 1 year old. That's why diapers are useful, so you don't fall down on the floor. You fall down on the diapers and then on the floor. Then the next interaction you come to know is electricity. When you put your fingers in the plug, in the electric plug, you should not do that, of course, but when you feel that, you get immediately impassionated by electricity if you don't die. Then I talk already about the strong force, which is mediated by gluons. The particles exchange are gluons, and this justifies the cohesion of the atomic nuclei. And the weak force behind some radioactivity processes, only some, not all, are mediated by the exchange of these particles, which we call bosons. Now, let me now tell you also that we know today that these two forces are unified at a very high energy in a single electroweak force. We would also like very much if we could also unify the strong force to the electroweak force. This was not yet able to do so. Or even gravity, because gravity, you see, is very, very weak compared to electric force in the nucleus, in the atom nucleus. And of course, there are many more fundamental interactions that we don't understand at all. Love, politics, sports, at all. We don't. Let me remind you, gravity is sometimes left out of the standard model of particle physics because this strength is very, very small. Also that the photon has no mass. No mass means infinite range for the interactions. That's why we see the light from the stars. Whereas these particles associated with radioactivity are so massive that the radioactive process occur mostly within the nucleus, the atomic nuclei, range extra small. And there is one final less explained force called associated to the Higgs boson, which is not a force between particles. So this exchange of particles, we call the particles exchange the bosons, photon, gluons, Higgs boson, or W or Z bosons. And the Higgs boson was discovered, well, 2012, and it is a very good demonstration of the existence of a medium permeating the whole universe called the Higgs field. And the Higgs field allows us to understand why these particles, how come these particles have masses like these values instead of zero. Zero, although you might feel strange that what is a particle with mass zero, but if I tell you that particles and waves are the same thing, a wave with mass zero is something that you understand, I think, very well. Electromagnetic wave has no mass associated to it. Now, waves associated to this boson should also have no mass associated to it, but they have. It's these huge values in these units in which the proton has mass almost 1, so these particles are 92 or 93 times more massive than the proton, and this one 130 times more massive than the proton. So how come they get mass? Well, we explain this exactly using the Higgs field. So I use this animation. Let me let me wait before, now I have to come back to the presentation. Pretam, are you seeing the screen or must I relaunch the share? Probably I have to relaunch the share.
Yes, we can see.
You can still see the screen, right? Okay,
yes,
so let me
yes,
go.
we can see.
So if you don't see the movie starting, please let me know, okay?
Of course.
But I want to put the sound off, that's why. Now I can restart it. Okay, you see the movie going?
The movie is not working, maybe.
Maybe that's why I thought maybe I have to restart the, let me relaunch, sharing. I'll stop sharing, I'll come sharing back again, okay?
Okay.
Coming back soon. You are seeing it now? You are seeing it now? Okay, you see it.
Now it's working.
So imagine it's working, but the movie stopped somehow.
Yeah.
I don't know. Okay.
Yeah, now it's working.
So imagine that the Higgs field is a group of scientists in the room. A tax collector enters the room. He does not talk to anybody, so he moves at the speed of light. And we say it has no interaction with the medium, with the people, so has no mass. But if a very famous person enters in the room, like Mr. X, he also wants to go very fast at the speed of light to the bar to get, say, one glass of good wine, but the people want to talk to him, and then he moves very, very slowly. He interacts very much with the medium, with the Higgs field, and then he moves very slowly. We say that he has a very high mass. So what we say is that things have a very high mass if they interact a lot with the field. So what is the Higgs boson? It's the equivalent of a rumor launched to the room. The people close to the door will make a clamp and discuss what the guy is speaking about. And then the others also become curious and they approach the others, and this clamp is moving in the room. Now, this clamp is the Higgs boson caused by the interaction of the people with themselves, of the field with itself. So remember, a particle does not interact with the field like this tax collector, we gain zero mass, whereas a particle interacting a lot with the field will gain a lot of mass. It's by interacting with the field that particles gain mass, and that's why it explains why these other particles have a large masses, while the photon that does not interact with the medium does not have any mass at all. Now, this Higgs boson, the exciting of the particle, of the medium to produce this particle that then decays immediately. So the words above were the discovery of Higgs boson into two photons. We can see in this image, well, an image that's not certain, but it's a candidate for the production of a Higgs boson in this center. And only by statistics, we know, by collecting a long, enormous amounts of these images, that we come to have the evidence that this indeed is the testimony of the Higgs boson. And it justified the Nobel Prize attributed to Peter Higgs and François Englert in 2013 for their theoretical discovery. But recall, only after the experiments confirmed the existence of this particle, because physics is an experimental science, and this was done at CERN's Large Hadron Collider, and CERN is the best laboratory to work in the world because a lot of people from their different cultures and expertises and languages work together on the same, with the same aim, with the same objective, and find the results. This accelerator is a picture of the accelerator at CERN, of the very large experiments with more than 4,000 physicists working on them to collect the data and to analyze the data. And in the center of these experiments, we are able to reproduce the density of energy or temperature conditions that existed 1 picosecond after the Big Bang. It's not a long time after the Big Bang. Now, the Big Bang explains our universe 13.8 billion or 1,000 million years ago. If you compress this in a year, makes also this very nice poster that would fit very nicely next to the other poster I advertised before. But coming back to real time, LHC can reproduce the conditions 1 picosecond after the Big Bang, but the conditions of energy density and temperature. And with this, we know that the particles there were only elementary. There were no atoms, there were no protons, no neutrons. There was only quarks, antiquarks, electrons, all those particles from that table before, and a lot of energetic, very energetic radiation. 1 microsecond after the Big Bang, the quarks joined to make protons and neutrons that the radiation could not break anymore. A few minutes after the Big Bang, these protons and neutrons gather nuclei that the radiation was not able to break anymore. And once you have nuclei, you can think that electrons are attracted to nuclei and build atoms. Yes, but the radiation is so energetic that atoms are destroyed by this radiation. So when do atoms actually become stable? 380,000 years after the Big Bang. 380,000 years that the radiation lost energy and stopped being able to break the atoms. And then you have hydrogen atoms that get together to make molecules that get together to make substances, and then stars, and then galaxies millions of years later. And this image of this cosmic background radiation is this photograph I show here of this cosmic radiation coming from different parts of the universe and reaching Earth. Well, I've talked what we know. I want to spend the next, say, 10 minutes to talk about what I don't know. So I put here an image in Braille to call your attention that sometimes we don't know, we must read in different ways, must get information from different methods to get more information. So this is the invisible universe. In Braille, I wrote in Portuguese. So this is the Braille, the translation of the Braille. So this is Portuguese, and this is English, the Portuguese, the translation from the Portuguese words that I put in Braille. And when we look to a galaxy like this one, with a telescope like the Hubble Space Telescope, we get this view. But if we use a filter, say an infrared filter, the image is quite different. And if we use ultraviolet, even more different. And we use X-rays, it looks like the galaxy is rotated. And it's not, it's still the same galaxy. But now we see some things that were not there before in this image. Some jets coming out of the center of the galaxy. And when you use radio waves, it's even more strange. There is a lot of gas coming out of the center of the galaxy that you don't see here at all. Now, this gas, it's not so impressive to me, the amount of gas. What's impressive is the distance that the gas must have traveled. Let me use a laser pointer. So you see, it just traveled almost 50,000 light years. So there is a very violent source at the galaxy, at the center of a galaxy, and we know now that it must be a black hole with mass above 100 million solar masses, between 100 million and 150 million solar masses, to be able to eject gas like this 50,000 light years away. Now, when we look to the movement of stars around the galaxies, we also find something extremely, stressful for us, is that the velocity of the stars is much, much higher, almost double, sometimes 5 times, from the velocity that we would expect from the mass of the galaxy that we see. Meaning that if they have these speeds, there is a lot more mass attracting the stars, mass that we don't see. It's not luminous, the mass that doesn't shine. What can it be? Mass that doesn't shine, not planets, we call it dark matter, matter that doesn't shine. Like the iceberg, well, you see the tip, the top of the tip, as the money of the Lehman Brothers scandal in 2008. Most of the money of people disappeared, and we don't see, well, you see the top part. Now, even in our galaxy, we know it exists because the sun is moving much faster than it should. And we know this matter, this dark matter that doesn't emit any kind of light, is distributed in the galaxy, is not aggregated in black holes or planets or gas or whatever, is not the form of any known matter to us. We have no idea of what is this dark matter. We know it must be some kind of substance, some elementary particle that we don't have a clue of what it is. We have no idea whatsoever. And then we have this problem that scientists went to measure the distance of distant supernova to measure the evolution of the rate of expansion of the universe. Due to gravity, we expect that the galaxies, faraway galaxies, the distance decreases with time because, the rate that the expansion, the universe is expanding, this rate decreases with time because, after all, the galaxies only feel attractive forces like gravity. But then they also found something different. They found that indeed galaxies are further away than expected. They have moved faster from us, at least in the last 6,000 million years, than they should. If they would expand from, if it would be a universe expanding at a constant rate, would be the dashed red line. What I would expect due to the gravity attracting the galaxies, that their speed of moving away would decrease with time, but is increasing, and this is mind-blowing. I mean, it's mind-blowing that the galaxies, the ones which are very far apart, are moving faster away from each other than I would expect from from constant expansion. So the expansion is accelerating. It's not decreasing, it's actually accelerating. But something must be overcoming gravity to explain this acceleration, and we have no idea of what it is. And the last proof that we have no idea is the name that we call it. We call it dark energy. Now, you can say that, okay, it's a small effect, because when I dropped something, it falls to the floor. It does not have this anti-gravity near me, certainly. And well, that's very good. Otherwise, we would all be floating and diverting from planets instead of being attracted to planet Earth. So it's a very small effect. Well, it's not so small. It's 70% of our universe. 70% of our universe is a form of, let's call it energy. We know it's as units of energy density, of which we know nothing about. Not that we very much know of the other 30%. Of matter, we don't know 25%. Of the universe is dark matter that we don't know anything of. In fact, of the universe, we only know 5%. So the amount of matter is 30%, meaning that 85% of all matter is this dark matter that we know nothing about. So it comes, well, physics is a very good discipline to be now, because there are so many questions and puzzles for us to try to understand. You might want to say back home that you want to follow physics studies, and people might tell you, oh, why? There is nothing there to be done. Already in the 19th century, these people announced that physics was totally discovered. After the discovery in the 19th century of thermodynamics, electromagnetism, and mechanics, there was nothing new to discover. There was only precise measurements to be done. But even this person with the name of temperature called the attention to two clouds in the landscape of physics, the black body radiation and the null results of Michelson-Morley experiments. And these two clouds were solved in the 20th century by the revolutions of relativity, of Einstein, and to quantum mechanics, of Planck, Einstein, and many others. So indeed, also today, it's funny that after the discovery of the Higgs boson, there was this famous physician that also published a book called The End of Physics, in which he stated that after discovering Higgs boson, there is nothing fundamental new to be discovered. But let me also, well, present a few questions to you, for you to answer, because it will be your generation that will be answering these questions. I'm already too old, as you might have guessed it from this talk. And there is not only two questions, there is a lot more questions besides dark matter and dark energy. There is a question of the matter-antimatter asymmetry. Why are we made of matter? Where is the antimatter in the universe, if it's any? Will the three forces unify? Are the elementary particles truly elementary? I mean, the ones we know today, electron, is really indivisible? Are the quarks indivisible? Or are they made of something smaller that we don't yet discovered? Okay, I don't resist to have some whys here. Why three families? But especially, why are the values of fundamental constants of nature so perfectly suited for us to follow this talk? Thank you very much for your attention. I'm now good for questions. I took 10 minutes longer than expected from my presentation.
And thank you
And sorry for the
for
problems with the
no,
video.
no, it's okay, sir. Thank you for your wonderful and exciting presentation, sir. I think students have learned a lot of things about these voyages of the universe. So we have got few questions. If you allow, we can start our questions and discussion, question and answer and discussion session. The first question: what is the quark-gluon plasma?
The question, well, quark-gluon plasma was supposed to exist at the level of this microsecond after the Big Bang. And it was proven to exist at the CERN experiments and Brookhaven, experiments at CERN and at Brookhaven in the United States. Whereas by colliding nuclei, in the case of CERN was lead against lead, creates, when they collide head-on, it creates such a dense matter, so dense, that the protons and neutrons basically are destroyed. And the only thing that remains are quarks, antiquarks, and gluons in a soup of quarks and gluons. And that's what we call the quark-gluon plasma. Now, this plasma, because also the nuclei are traveling very fast, so this collision is taking place very fast. So the plasma is created very, very quickly, and also very, very quickly, it immediately is fading away. So it's creating other particles, and the quarks are joining again together to create another protons, neutrons, and other lots and lots of particles. And then the plasma dissolves almost immediately. So it's created in a very single condition of time and space to fade away immediately after, very, very quickly. But we know that this state is creating these head-on collisions, but only when they are head-on. So if the nuclei, if lead nuclei travels a bit side by side, then it's not created the plasma because there is not enough particles interacting. It's only when the collision is head-on that you create so many particles together, flying at so strong speeds against each other, that basically you destroy the kind of membrane around the proton and nucleus, and you have this soup of quarks and gluons that dissolves very quickly afterwards.
Thank you, sir.
Second question.
We have another question. Yeah, what is the Higgs boson?
What is the, what, can you repeat?
Higgs boson. Higgs
Yes.
boson.
What's the question about the Higgs boson?
Yeah, just what it is.
Ah, so the our theory of masses of elementary particles does not allow to have these waves with mass, and the electron is a wave. Sometimes behaves as a wave, sometimes behaves as a particle. So if you cannot have particles with masses, how can you explain the mass of the electron? And the reason is you're explaining by having the wave of the electron interacting with the medium being the vacuum. But there must be something there besides vacuum, otherwise you would have no interaction. So what is there besides vacuum that provokes this interaction? It's the Higgs field. So the Higgs field was proposed in 1964 exactly to explain how elementary waves could gain mass by interacting more or less with this field, with this thing permeating all the universe. Now, of course, this is a fantastic idea because then you don't have something made of nothing. Elementary particle is made of nothing, is a point thing. So there's nothing in it, just a wave. And made of nothing could not have matter in it to have a mass. So how do you put mass in it? And then you say you put mass because it interacts with the medium. Interacts more, moves slower. Interacts less, moves faster, does not interact, moves at the speed of light. This is a fantastic idea, but we would have no reason to support this idea if we don't find the particle associated to the medium. And the particle associated to this medium is the Higgs particle, the Higgs boson. So the Higgs boson is the particle associated to the Higgs field that fills the universe. So you can think of the Higgs boson as a local excitation of the field, like waves in the sea, when the sea is mostly flat. But when you have very, very strong waves colliding, you see a wave coming up and going high. And then when you see a wave coming high, you see, I saw this would be the excitation of this medium would create the Higgs boson that decays immediately. So that's what is the Higgs boson. The Higgs boson is the interaction of the media with enough energy between itself that creates this clump of energy density, which is the Higgs boson decays immediately. I hope I've explained it more or less well, Pretam. You correct me.
Yeah,
If I have to
thank you,
improve the
sir.
explanation, let me know.
Okay, so we have got another question. Uh, can neutrino takes us to the one of the greatest voyages of the universe by revealing many of its secrets?
You have to talk slower. Maybe you can
Okay, so
write in the chat the
I can
question.
I can add the question in the screen. You can.
Okay, yes. Yes, there is a lot of research on neutrinos with many groups in my laboratory, but also in many other places. And these neutrinos we also know very little about. So let me come to my presentation. Let me stop sharing. Oops. And now come to the presentation. No, I have to do this. Okay, now I can stop share. And how do I move it? And I want to go to my. Now I have to go back here. I want to show you my table of particles. For this, I need to put this in another screen. Then I come back to my screen and I share the other screen. And I'm going to share. Okay. Now I can get back to my screen and show you this table of elementary particles. Now you see here, I hope you see.
Yes, we can see.
But you don't see my mouse. I want you to see my mouse. How do I show the mouse there? Let me put the pen something. Well, let's talk about the rows. In the first row, you see lightest neutrino. In the third row, you see middle neutrino. And the fifth row, you see heaviest neutrino. It only tells us that we don't know very much about these neutrinos. And actually, neutrinos, we don't even know if they are or not, they are antiparticles. If the anti-neutrino is not the neutrino itself, we don't know this yet. So we have experiments going on to study these neutrinos, to study what masses they have, because we found out like 20 years ago that they must have masses. We just don't know what masses they have. And there is a lot of knowledge to be known from neutrinos, also from the neutrinos from the Big Bang, from this initial enormous emission of neutrinos that we are not yet able to detect, but we will be able, I don't know if we will be able to detect in the future, we hope so. So we are doing a lot of research of these neutrinos and finding out what they are and how they behave. But there is much to be learned also. Pretam, next question.
Yes, the next question is, okay, 1 minute. So, which is the smallest subatomic particle known to us still now?
Is the electron or all these particles in this table plus these ones. These ones and these ones. These are the elementary particles. They don't have size. So in terms of smallest, these are the smallest known to us. But when you think something does not have size, it only means it does not have size to our microscopes. And the microscopes only can tell on a distance which is smaller than this. It's at the level of 0,1901 of the meter, 10 power to minus 20 of the meter is the smallest size that we can test with today's experiments. So the only thing we can tell is that these particles here, in particular the quarks, even the heaviest quark with 185 times the mass of the proton is elementary, is the size of the electron, if it is any size at all. We say it is zero size because we don't know. We only know it's smaller than 0.0000, well, 19 zeros, 1 of the meter. We cannot tell anything else because our microscopes are not going small enough. But we don't know. If they are made of smaller particles, we just don't know. It's for you to know
Yes.
with future experiments.
So thank you. So we have another question. So are all the subatomic fundamental particles made up of something which are nearly equal to the Planck's length?
We have no idea, nor we have a way to answer that question yet, or very in a long time in the future, because the Planck length is so small. The Planck length is 34 zeros after the comma, and I was discussing 19. So we still have 15 zeros to go to the Planck length. So we clearly have no idea of models that would bring particles or objects of that scale that would constitute the other particles. We just don't know. For us, in all our experiments, these particles are still behaving as elementary, as pointless, or as point particles, as zero size.
Okay, sir. So we have another question. So, sir, is it possible the collision which happened in CERN can any effect on space-time which detected by LIGO?
No, not at all. The collisions inside CERN, although having energy highly concentrated in a very small volume, the total energy, well, is not big. The collision energy is not big in terms of joule, well, macroscopic size. They are not. And the LIGO detects gravity waves. Well, and gravity is extremely feeble effect. So there is no way that CERN would create collisions that would make detectable gravity waves in the other side of the planet. But even if the experiment was close to CERN, they would detect gravity waves from electromagnetic induction than from gravity waves themselves. So they would not be able to distinguish from other effects, even seismic effects. So no, collisions created by CERN would not give information to LIGO other than exists a Higgs field and a Higgs boson.
Thank you, sir. We have another question. So, why dark matter is different from baryonic matter? What could dark matter be?
No, it's not baryonic matter. It's different from baryonic matter. It cannot be baryonic. And we have
Why,
no
sir?
idea.
The question.
Baryonic matter involves quarks, which have a strong force. And one thing we know about dark matter is that they don't have any, well, they have a very small force between them. Certainly gravity affects them, because that's how we know it is there. But we have no, well, they don't have strong force, because if they would have a strong force, they will be all glued together, and they are not. So they don't feel the strong force. They don't feel electromagnetic force, otherwise they would emit light or absorb light, and they don't. So the only remaining forces are gravity, these we know they have, and weak force, which we have no idea if they have or not have, or what intensity they have. It's our hope that dark matter does have or sense the weak force. Otherwise, all experiments proposed to discover to discover dark matter are somehow compromised. At least one type of experiments, the experiments of direct interaction of dark matter with a medium, would be compromised if they don't interact other than gravity. If they only have gravity interaction, it's a bit of a problem for the discoveries of dark matter. A huge problem, not a small
Okay,
problem.
sir. Thank you. Yeah. We have another problem, sir. Is the ether theory and Higgs field are same?
Is the Higgs field and
And ether theory.
no, not at all, not at all. The ether theory was proposed because people could not think of electromagnetic wave without a medium. whereas the Higgs, but it did permeate the universe, but it was measured that it could not be as a medium in the universe that the planet Earth would move around and would not differentiate the propagation of electromagnetic waves. So in that sense, ether theory was completely discarded when Einstein brought about his idea of a constant speed of light for all frames of reference. And this basically destroys ether theory. Now, related to the Higgs field is totally different thing, because the Higgs field is permeating as ether theory all universe, but now it's not about difference in waves propagation. The waves that propagate one direction or the other, they would all feel the same interaction with the Higgs field. So you see no difference upon the movement of the planet Earth among the field. The Higgs field is the one that gives mass to the particles. And for example, if the electron would not interact with the Higgs field, it would not be coupled to the nucleus. It would escape the nucleus, and we would have no atoms. And if you have no atoms, it's a bit of a disaster for us. So the electron has this interaction with the field, so we know the field exists already at the nucleus level inside our bodies and around us. And we know it permeates the whole universe, but does not affect macroscopic bodies, of course. I don't know if this answers the question of...
Yeah, thank you, sir. This may be the last question. So,
Okay.
we know mass of the neutrinos. What about the mass of a 3-generation antineutrinos?
Now, the antineutrinos are, if they are different from neutrinos, are the antiparticles of the neutrinos. So in the table as shown here, for each particle, there exists an antiparticle. Now, what we don't know is if the neutrinos is the same particle as the antineutrino, like the photon. We know that the photon is the same particle as the antiphoton. So we don't talk about antiphotons because they are the same as photons. Also, if you like, maybe I can. Am I sharing the screen? I stop sharing. Okay. So if I show here the other table. Okay. Here you see a photon, the W's and the Z's, the gluons and the Higgs. Well, all the antiparticles of these particles are the same particles. So the antiphoton is the same as the photon. The anti-gluon is the same as the gluon. The anti-W minus is the W plus. So it's not exactly the same, but you could talk about the W minus traveling one direction or the W plus traveling in the opposite direction. And the anti-Z boson is the same as the Z boson. Now, this is not yet the case for neutrinos, as far as we know. If neutrinos are the same as antineutrinos, we would have to revise the model, because we don't know that in the model. In this model, we expect that the neutrinos and antineutrinos would be different particles. The opposite of each other, but different. We don't know that yet. Now, what we know is that the mass of the particle is exactly the same, the mass of the antiparticle. And this is a requirement by mathematical theory. So the mass of the positron is exactly the same as the mass of the electron. For these elementary particles, of course. In composite particles, it is slightly different, the antiparticle from the particle, and that's what's behind the matter-antimatter asymmetry. I don't know if I explained it well, but...
Thanks for your wonderful and exciting presentation and nice discussion session. The main aim of our program is to motivate and encourage our students. I think by your lecture, some of our students have definitely motivated in this research, and hopefully in the future they will join in this research field. As we know that
so.
Almost 95% of our universe is unknown, and that is dark matter and dark energy. So we have to find out that things, and we have to do that research. So we are trying to encourage our students. So thanks for giving us this opportunity to arrange such an exciting webinar, sir. And we would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation.
Dr. Pretam, I thank you for this opportunity to engage more students to answer those questions that we are,
Yeah.
well, we are lacking time to solve
Yeah.
them. So we need the next generation.
Yes. 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 And you have already mentioned the question, some unknown question that we have to solve, and
Yes.
that is the aim of our recent modern scientists. So we need to know these things, and we are also trying to encourage our student, and that the intention of all scientists. So thanks, sir, again for making this webinar interesting and exciting, and hopefully in near future we can arrange another webinar with you, sir. Bye for today.
Okay. Looking forward
Have
to
a
it.
nice day,
Thank
sir.
you very much, Dr. Pretam. See you
Bye, sir.
sometime in the
Good night.
future.
Yes, sir.